So in exercise 2, we want to prove that the set G, defined as all elements n such that n is equal to 10 times k for some k in Z, is a group under addition. And when you get a problem like this, the first thing that I would do is I would play with this a little bit and convince myself that I know what group I'm talking about and how this group behaves. So before we prove anything, let's just play around with this a little bit. What are some things that are in G? So G is all n such that n is equal to 10k for some k in Z. So what if k is 1? What do we have? We have the element 10. 10's in here. What if k is 2? Then we get 20. What if k is 3? We get 30. And so on. K can be an integer. So k could be 0. If k is 0, I get 0 in here. And if k could also be negative, so I have minus 10, I have minus 20, I have minus 30, and all of those numbers in there. So what do you notice? How else could we describe G? Looks like we are looking at all the multiples of 10. That's our group G. It's the set of all multiples of 10. Now, do you believe that that's a group under addition? What do we have to show to show that something is a group? We have to show closure. We have to show associativity. We have to find an identity. And we have to have inverses. And again, before we prove anything, let's think about closure. When you take a multiple of 10 and add another multiple of 10, like you have 20 and you add 50, you get 70. And yep, the ones digit is 0. So apparently, I could convince myself that that's true in general. That's not a proof what I wrote down, but I'm convinced. Associativity, we get that again for free because, again, we are looking at a subset of integers. So we are looking at a subset of integers, and addition is associative among the integers. Do we have an identity? Indeed we do. It's 0. We listed it. And adding 0 to anything else in our set will leave the other elements alone. So looks like 0 is the identity. Do we have inverses? Let's see. So here we have 10 and we have minus 10. Combining those two, adding those two will give us 0. And same with 20 and minus 20 and 30 and minus 30. So the way we listed our group elements, it really looks like we have inverses. They come in pairs. So yes, let's convince ourselves. So that's just the scratch work right here. That wouldn't get you very many points on an exam or on a homework assignment. We actually have to write the proof. So let's see what that proof would look like. But the scratch work, it's very important, right? It's very important to get an idea for what we are talking about, to really be able to picture what's going on in this problem. We can write down things in the same order that we wrote them down over here in our proof. So first we are going to look at closure. Okay, so for closure, I grabbed 20 and 50, but we could have picked any two numbers, and we have to pick arbitrary numbers. So let's choose any elements m and n in G. So what has to be true then? Well, they have to be multiples of 10. So let's say m is 10 times some k1 and n is 10 times some k2. I could have picked anything, k and l, a and b, doesn't matter. I picked k1 and k2. And k1 and k2 are just integers. Okay. So then, what happens if we add those two numbers? So m plus n is equal to 10k1 plus 10k2. And where are we going with this? We have to demonstrate that m plus n is in our group G, in our set G. And what puts something into G? Well, it has to be a multiple of 10. We have to write it as 10 times an integer. So there's one more step here. I have 10k1 plus 10k2. I can factor out the 10. And I have 10 times k1 plus k2. And since k1 plus k2 is an integer, then 10 times k1 plus k2 is an element in our group. So that gives me closure. Now, how do you write down associativity? Associativity. Pretty much the same way we did before. So G is a subset of Z. So the associativity in G follows because addition is associative already in Z, and so it's associative in any subset of Z as well. Now the identity. What do we need to show? We need to show, well, we need to find it first, and we already identified it at 0. So what's there to say? Well, 0 is equal to 10 times 0. And so since we can write 0 as a multiple of 10, it lives in our group. So 0 is an element in G. So it's in there. And we have to show that it behaves like an identity element. So 0 plus n is equal to n plus 0 is equal to n for all n in our group G. And so we can conclude that 0 is the identity element. So we have to show, first of all, that it's in G and that it behaves like the identity. And then inverses. We already identified how to find them. So, but we have to show that this works for any element in G. So let's choose any n in G. So again, let's say that n is equal to 10 times k. For some k in Z. So this is just, again, describing what an element in G looks like. And so what is the inverse? What do we propose is the inverse? Well, 20, the inverse was minus 20. 30, the inverse was minus 30. So for this k right here, that needs to be minus k, and that gives us our inverse. So let's write that down. Since minus k is also in Z, and 10 times minus k is in G, so minus k is in Z, then 10 times minus k is in G, and so we have 10k plus this new thing, 10 minus k. That better be our identity element 0. So, but there's a step that we have to put in between here. So we have 10k plus 10 minus k. That's the same thing as 10k minus 10k, and that we know is 0. Okay, so 10 minus k is an element in G and is the inverse of n. Technically, we also have to show it from the other side, but that would also be the case. So we have 10 minus k plus 10k is also equal to 0. Excuse me. And so again, we showed that those 4 things are true to prove